So now we're going to look at a chi-squared hypothesis test. So going back to binomial, we haven't talked about binomial in a while, but keep in mind binomial has two possible outcomes. So this specific hypothesis test we're about to look at has more than two outcomes. So it's under the category of a multinomial experiment, which means there's a fixed number of trials that we are doing something, but there are more than two possible outcomes for each one of those trials. So you can kind of think of it as almost like a multiple choice test, or any kind of survey where you have multiple items to pick from. So the probability for each one of those outcomes is going to be fixed, and they're going to be classified into categories, each of our outcomes. So here's the things to focus on. Now that we've done one sample and two sample hypothesis tests fully, there's only a few pieces that we are really looking at within chi-squared tests. So the ability to find both the observed and the expected frequencies, and we'll make a nice little chart out of that. How to find the critical value, which you will be using a table for. It is not from your calculator, this value. The test statistic, there's a formula, and then just the decision at the end, whether we are rejecting or fail to reject. So our chi-squared goodness of fit test has a set hypothesis that we are testing here. Our null hypothesis is stating that our frequency distribution is going to fit the expected distribution. So it's fitting within what we are expecting. Then our complement to that, our alternative hypothesis, is that it does not fit. So it doesn't fit our expected distribution, or doesn't fit the claimed distribution. So you can kind of think of this as almost like an equals, not equal scenario. Either it fits or it doesn't fit. In order to do this chi-squared goodness of fit test, we have to have two conditions met here. Our observed frequencies must be from a random sample, and each one of our expected frequencies must be greater than or equal to 5. So that's saying that each one of them, we expect at least 5 from each. So we would have to check that for each one of our categories or outcomes. Now, if your conditions are met, we can find, again, that critical value with our chart using k-1 degrees of freedom, k standing for categories. So however many possible outcomes you had, -1 for your degrees of freedom, and then your alpha is the other piece on that table. Whatever is given to you is the one you use. Our test statistic formula is here in the middle in red. It is chi-squared is equal to the sum of O minus E squared over E. O and E are standing for your observed and expected frequencies. So we'll see how to find both of those in just a moment. And as far as the sketch and your critical value are concerned, these are right skewed and right tail shaded. So all of your chi-squareds are going to have a rejection region over here on the right, and then fail to reject on the left. Your observed frequencies, so this is our variable O, are going to be given to you. This is what they have found when they went out in the sample data and gathered our survey results. These will be given to you somehow. It might be in a paragraph written out, or it might be already in a chart. But these are the individual survey results already given to you. Your expected frequency, the variable E, you will have to find. So you will be given a list of percentages for each one of our expected outcomes for each one of our categories. And you're going to take that percent times the total sample size we have. So that is N times P, to find the expected value, what we expected to occur for each one of our categories. So you're going to do this for each one of your categories, and we'll fill it into the chart right next to what we observed happen for each. So we're comparing the O's and the E's together to see how far apart or how close together these values are. So here's our first example. It says a retail trade association claims that the tax preparation methods of adults are distributed and shown in the table at the left which will be on our next slide. A tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. The results are shown in the table at the right below. At a level significance of 0.01, test the association's claim. So we are testing to see if this fits what we expected or not. So these would be the two different charts that were given to you. Now again, keep in mind, HO is that we are fitting in that expected, and HA is that we do not fit. Looking at our values, we have a list of percents and we have our survey results. So we're going to kind of combine this together into one chart where we are going to list out all of our observed values and our expected values together. So again, observed are things that come from your survey results. These are the numbers that out of your sample size, this is how many fell into each one of our categories. So for us, that is these values right here. These are your observed values. So for the accountant, we observed 63 people said they use an accountant. 40 people said by hand, and so forth. Observed values will be given to you. Your expected values are going to come from your percents times your sample size. So for us, our sample size was 300. So we're going to take each one of those percents times 300. Most of these are going to come out as whole numbers. If they don't, try to keep as many decimals as you can so the numbers work out well. I always recommend 4 decimal places. For these, 24% times 300, we get the number 72. Then we do 20% times 300, we get 60. Don't forget, with percents, you're not actually multiplying the number 20, you're multiplying 0.20. And then 0.24, 0.35, and so forth, 0.06, and 0.15. So when we multiply 35%, we get 105, and then we get 18 and 45. Your expected value should still add up to the original sample size. So if you wanted to check those, you could add them up, and we do equal 300. Now we've found the observed, we found our expected. The next thing we need to do is our critical value. Again, this is a right skewed, right tail shaded graph. If you land in that shaded space, that is your rejection region. If you land in the not shaded space, that's when we fail to reject. In order to find the critical value, we use the chi-square table, and we need 2 pieces of information. We need the alpha that was given to you. So in this problem, it was 0.01. And the other piece we need is degrees of freedom, which can be found from K minus 1, where K is your categories. So categories meaning accountant, by hand, computer software, friends and family, tax preparation. So there's 5 categories. 5 minus 1 is 4. So those are the 2 numbers we're going to use on our chart. You're going to go down on the left-hand side to a degrees of freedom of 4 and use that row. You're going to go across the top to the right till you find an alpha of 0.01 and use that column. So you're going to line up your row and column, and you get the value 13.277. That is your critical value. That's where that shading starts and stops on your graph. So if we get any number bigger than that from our formula, we will reject. Any number smaller, and then we would fail to reject. So the last thing we need is our test statistic, our formula. Keep in mind these values from our table. And in fact, I'm going to copy them over here just for our ease of seeing them. Our formula is going to take just these two values, O's and E's, and we are going to subtract them, square them, and divide by E. So O minus E squared over E. And the sigma in the front means you're going to do it for each row and then add them all up. So 63 minus 72 squared divided by 72 plus, and then we do it for our next row, 40 minus 60 squared over 60 plus, keep in mind, and I'm going to have to go on the second row because we got two more to do, only the top is subtracted and then squared. So the square does not reach the whole fraction. It is just the answer from the top. This is a great time to practice with your calculator using the alpha y equals. I'll put that at the top. Alpha, and then the y equals button. To type in a fraction, you should see a nice little pop-up window that gives you the option for n over d. And that's where you would type in a numerator over denominator. You can do that for each one of our categories or our rows from our chart. You want to get all of that information typed in one go, click enter one time, and then round your answer off to 4 decimals. So we get 16.8885. This is our test statistic formula, answer. We compare this back to our critical value, our sketch. We are bigger than our rejection region, so we would reject. Reject HO is our decision. Those are the pieces of information to focus on. Finding your observed and expected, your critical value from your table, be able to do our formula for our test statistic, and make a decision, reject or fail to reject. Now, the one other thing that will come up in this section is a unique situation that's called uniform. So let's read this last example. A researcher claims that the number of different colored candies and bags of dark chocolate M&Ms is uniformly distributed. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown in the table. Identify just the observed and expected frequencies. So we have a chart of all of the colors of M&Ms and the frequencies that have been found out of the 500 M&Ms we've looked at. So I've copied this over to our next slide. Again, our sample size is 500. So if we're going to fill in a chart of our observed and expected values, what we were given here is the observed values. This is what we already know. So we've got 80, 95, 88, 83, 76, and 78. Those are our observed values. Now, typically with expected, we use N times P, so your sample size times each percent, but we weren't given any percents on this one. We don't know the division between the different colors, but instead they give you the word uniform. Uniform will show up when you don't have the percents, because instead of the percents being something different for each group, uniform means they are all the same. So that means there's an equal likelihood that we would get a brown one to a green one to an orange one and so forth. So this is going to be uniform, meaning the same expected value for each. So in a situation like this, the easiest way to find the numbers that go in the chart is instead of N times P, because we don't have P, you're going to take N divided by K. N meaning your sample size, so in this case we have 500, divided by how many categories we have. We have 6 categories. So if you take 500 divided by 6, you get 83.3333, repeating. So that's the expected value for every single row. It should be the exact same number for all of them when you have a uniform distribution. So uniform, again, means that your expected values should all be the same. And when you do have a uniform, you can find your expected values by using N divided by K, your sample size divided by your categories.